Applications of rational inequalities. We're just going to jump right into this skill with an example. So we're going to take the function c of x is equal to 10x plus 3,000 to represent the cost to produce x number of iPhone cases. We're going to create a function c of x to represent the cost per case produced. Now, this c of x is a lowercase c, the other c of x was an uppercase c, so this c of x is going to represent the cost per iPhone. Well, all that really depends on is the cost for x number of cases, and we divide that by the number of cases. We have both of these already. This is the function capital C of x, the cost to produce x number of cases, and the number of cases itself is just x. So the function to represent the cost per unit is 10x plus 3,000 divided by x. So that's our function c of x. So that's how we're going to begin. That's a quick example of writing a rational equation or a rational function for a situation. And now what we're going to try to do is to solve an inequality problem that uses this rational function. Now here in the second part of this question, we want to write an inequality to determine the number of cases that need to be produced in order to keep the cost below $15 per case. So here's our inequality. We need to keep the cost below $15 per case. So that means less than and not equal to, because it has to be less than 15 to be below 15. 15 is not below 15. So less than $15 per case. And as we did in part A, we have an expression for, or a function for, the cost per case depending on how many cases are produced. So this would be c of x. The cost per case has to be less than 15. So writing c of x as the function it is, that's 10x plus 3,000 divided by x must be less than 15. So this is that inequality that we want to solve. And so let's go ahead and solve this just like we've solved every other inequality so far. Same methods. So to begin with, we're going to make one side of the inequality 0. So we subtract 15 from each side. And that leaves us with 10x plus 3,000 over x minus 15 is less than 0. And now we need to combine this into a common one fraction. So multiply 15 by x over x to give that term the same denominator as the other expression. So now I have 10x plus 3,000 minus 15x, all of which is over the same denominator, x, and that's less than 0. Well, simplifying this, 10x minus 15 is negative 5x plus 3,000 is all over x is less than 0. Now we don't need to factor the top or bottom of this expression because each is a linear expression. Negative 5x plus 3,000 is only equal to 0 at one place, and x is only equal to 0 at one place. So we don't need to factor any, but we could factor a 5 out of the top if we wanted to. But at this point, all we need to do is determine the critical points is to figure out where's the top of this fraction equal to 0 and where's the bottom. So let's carry on over here. We're going to go critical points. Let's start by figuring out or writing the equation we need. So where's the top of the fraction equal to 0? And where's the bottom of the fraction equal to 0? Well, that one's easy. There's no solving we even have to do for that one. And solving the first equation, I will add 5x to each side just to keep all my numbers positive. So I have 3,000 on one side, 5x on the other, divide by 5, divide by 5. And so this gives me the critical point of x equals 3,000 divided by 5 is 600. And also x equals 0 from there. So those are my two critical points for that inequality over here. So now I'm ready to go ahead and put these guys on a number line. So I put my number line down and we go 0 and 600 and we could go ahead and pick some test points on the left hand side of 0, but there's really no point. We know that we can't have negative numbers of cases. We can't produce less than 0 cases. So I'm going to go ahead and just X out the left of 0 already. It just doesn't make sense with the context of the problem. So really the only two zones we have to test are between 0 and 600 and after 600. So we'll go ahead and pick our test points. We could pick something in the middle of the zone, but I'm just going to pick 1 because that should be a pretty easy number to throw into my calculator and see if it fits in that inequality. So that'll be my first test point. Let me do it in purple here, 1. And then picking a number after 600, I'm just going to pick 700. No particular reason. I could have picked 701, or 601, but I'm just going to pick 700. So those are my two test points. So now I plug them into the inequality over here to test these 2 points. So is -5 times 1 plus 3,000 divided by 1 less than 0? Well, on the top I have 3,000 minus 5, that's 2,995 over 1. It's just 2,995. Is that less than 0? No. So that middle region between 0 and 600 is not going to work. Now let's test the same thing with 700. So -5 times 700 plus 3,000, all of which is over 700. That's my test point. So just plugging into my calculator, what does that top expression equal? That's -500. -500 over 700. I'm not even going to worry about calculating that as a decimal. I can see that that's a negative number. And it's a negative number that is always going to be less than 0. So that region to the right of 600 works. 600 itself will not be an acceptable solution because we know that this has to be less than 15 and not equal to 15. So because of that less than, we exclude 600. And so it's every value to the right of 600. So because this is a word problem, we could either write our answer as a inequality. So we could say x is greater than 600. But even better than that, we should interpret that or write it as a sentence. So we can say that at least, and actually no, we shouldn't say at least, we should say more than 600 iPhone cases should be produced to keep the cost below, I'm going to use the word that was in the sentence, below $15 per case. And that's probably the best way to write our answer to this problem. Interpret that x, oh, and I made a mistake there. Oh, no, I have that right. X is greater than 600, so more than 600 iPhone cases should be produced to keep the cost below $15 per case. Just to finish up this example, I want to show you a graph of the function that we wrote for the cost per case. If you go to a graphing tool like Desmos, in this case I use Desmos, and type into Desmos, instead of writing C of x, if you just write y equals 10x plus 3000 over x, you'll get a graph, and I'm just showing you the positive x values of this graph because, like we talked about, it doesn't even make sense to have negative x values. So this blue line represents the cost function c of x, which is the cost per iPhone. And what you can see is that when you produce just a single iPhone, like let's say c of x is equal to, or x is equal to 1, so the cost to produce one iPhone, well, that's 10 plus 3,000 divided by 1. That's a cost of $3,010 per case. In this case, per one case. So it costs you $3,000 to produce a single case because this fixed cost is so large that no matter how many cases you make, you're always going to have to pay that $3,000 up front. But as you produce more and more and more cases, like when you produce, say, x equals 300 cases, the cost for 300 cases gets a lot lower because now you have 10 times 300 plus 3,000, all of which is divided by 300. And if we type that into our calculator, we can find this precise value that we can sort of estimate from the graph. Actually, maybe it's a really nice even value. I think it is. It'd be 10 times 300, which is 3,000, plus 3,000, divided by 300. So that's exactly $20 per case. And you can see that that's actually $20 exactly on the grid point. So as you produce more cases, we spend less per case, basically because we are flooding this 300 or 3,000 constant value by producing more and more cases. This 3,000 initial cost becomes less and less significant. Now, this graph, you can see that the change is really dramatic here for the first few hundred iPhones, but that it becomes much less dramatic as we go from 300 iPhones towards 500. And then eventually, as we get to 600, we hit that value we were interested in this problem, which is that when you make 600 cases, you get to exactly $15 per case. And it continues to drop from there, although slower and slower and slower. And it will never get to 0, in fact. Because if you think about it, even if you produce 1,000,000 cases, you still have this $3,000 upfront value, so they'll cost less and less and less and less per case, but they'll never equal 0. So I just wanted to show you that if we were to graph this equation, c of x equals 10x plus 3,000 over x, we can also see the solution visually, and this dotted line here in orange represents that y equals $15 value. And you could also use it to very quickly see what other kinds of costs would you have for producing other numbers of iPhones. So sometimes graphing is a really good way to solve these problems because it also lets you go beyond just the value you're interested in and consider other possible cases for, if you want to raise or lower the number of iPhones that you're producing, you can see just very, very quickly how much it would cost you.